who's going to speak about preservation properties, preservation of partition properties and their products.
Thank you so much for the invitation to speak. Very happy to be sharing these results, and sorry not to see a little bit of Toronto this time of year. So where I live in the fall, the leaves don't so much change color as crumple up and fall off the trees. So we've had 85 degrees Fahrenheit in this past week. So I think the trees are always a little bit confused. Okay, so I noticed that my title was very alliterative, so I joked that we could call it P to the fourth. This is joint work with my colleagues Vincent Gingona and Miriam Parnas, both at Towson University. And let me tell you where you can find, let's see, if you're looking for a preprint with more details on this work, it's available on arXiv. It's called Products of Classes of Finite Structures. So I'm only going to talk about some of what is in the paper. Vince gave a talk on this work at the University of Maryland Logic Seminar in September. And actually, if you're around there, Miriam's going to be giving a talk on some related independent work in the seminar at the end of November. So first off, I want to say that I was really happy that Vince and Miriam invited me to join their project. So they've been working for a while on these K configurations, which I'll explain in the next slide. And so that's very much their thing. And they had developed it in a previous paper that's also on arXiv. But they were looking for more examples for the age K. And that definitely overlaps with my interests. And so we got to talking about some constructions, and then this paper came out of it. So I'm going to talk more about the part of the paper that has to do with the partition properties, which was more my stuff. They did a lot of work on the configurations, and there's some disjoint and amalgamation stuff in there too that they did a lot of work on. So this is going to highlight mostly my interests and my work in the paper. So I'll start with the background on the K configurations and the K ranks. And this is really from my perspective as a non-expert, but I thought that might have some value because maybe I can give some motivation as I see it. And then why were we looking for these partition results? So we studied these two products that have come up previously in the literature, but just to highlight the relationship with the automorphism groups, we call them wreath and direct products. In some cases, we eliminated linear orderings that were there before. Okay, so here goes. So the K configurations. So the definition in this form is in Vince and Miriam's paper, their prior paper, which is also available on arXiv. And so the K configuration is basically supposed to capture an encoding of the finite structures in K somewhere definably in the structure M. So as you can see, it's very much related to dividing lines. Do we admit a definable order? Do we admit a definable graph relation? So basically, they're assigning for every relation symbol in the signature on the K side, the index side, they're going to assign some formula with parameters in the big model. Okay, so R goes to I of R. And then there's going to be this correspondence that, you know, if you have an edge over here, then the image in the monster model is going to satisfy the formula and vice versa. So that's what it is to admit a K configuration. And again, the examples to have in mind are if R is a ordering relation or a graph relation. And for all theories T that admit a K configuration, we call that class CK. So in their previous paper, they had studied these different classes and also match them up with well-known classes of theories that correspond to dividing lines in classification theory.
So Lynn, is n fixed all the time?
No, it shouldn't be. So I think I just wanted to make it fit on the slide. So I should have said that verbally. So I have to remember to say the verbal things. So
So for each a and k, there's a different n.
there should exist an M. Okay, let me pull up. This is their stuff. So I knew I needed to get this one right with the quantifiers. Okay. So this would be called a K configuration into M to the N. Right, so if there exists an N that has the order on N tuples, then the theory itself admits a K configuration. So as I understand it, the definition is K configuration into M to the N. So the N is indexing it. And then to admit one, there has to exist an N. Because the partial type on the M side, right, it could be on N tuples. Okay, did that address it?
Yeah, I think so. But so the formulas are n formulas. That's important, right? Like this I, the I takes an L0 relation. Like if the L0 relation has like x in it, and the x will become x to the n. Like n tuple, sorry. The one variable in L0 will become a tuple of n variables.
Yeah, right. Yeah. So okay, so if it's x, y, then you would have this tuple over here, like that.
Yeah.
Yeah,
But that's
okay.
a condition on I. That's condition on number one, because a priori number one is just some function, but it's more than that. It's preserved, like it has this, and goes into that. That's what I'm saying.
Yes, I think that has to be true. Yeah. Okay, and then that's my apologies. I literally was trying to make this fit on the slide, and then I probably cut out something I needed. Okay, so of course, the starting point is classification theory. So the characterizations of stable and NIP theories. And so in my work, I had tried point-by-point generalization of the characterization of stable theories to NIP. And it just worked because by the Neshtel-Rodel, Abramson-Harrington theorem, the class of all linearly ordered graphs forms a Ramsey class. So Shellich's same argument works. Okay. So what Vince and Cameron Hill were working on was, well, maybe we don't need K to be a Ramsey class. And so they have this more pared down definition. And so as you see, to be stable is not to admit the configuration from finite linear orders. The NIP is not to admit the configuration here. And then they verified the same thing from Chernikov, Palestine, and Takeuchi's work for hypergraphs. Okay, and so just to give some idea that they, why were they looking for new ages? So they were looking at this free superposition defined in Budirsky's work. And it's basically the structures that reduct to something in this class and something in this class. And such a structure is a free superposition of those two reducts for some bijection between them. And so they had looked at creating a rank from this. And so basically the idea is the partial type in T has K rank N if it admits the n-fold product, n-fold free superposition configuration. So that could be n independent orders, but not the next value up. So to be rank 0 is not to admit a configuration at all. And so they had, in their previous paper, looked at when T has NIP, and then this linear order rank is OP dimension. So there's something that Vince and Cameron had worked on. And so then that would mean that this rank coincides with DP rank in distal theories. So I guess what they're looking to do is try to capture some of these known ranks, but then they have some control over the configuration, and it allows them to do these rank calculations. Okay, so I think that tells a little bit of the story of why we were looking in this direction. So for example, they're able to uniformize. So if they have age indivisibility of the class K, then they can uniformize the type here on the target side.
Can you remind what age the indivisibility means?
Yeah, unfortunately, it's on a later slide, but I can. Here we go. So you could have some equivalent definitions. I think the shorter one, there are equivalent definitions in the El Zahar and Sauer paper, 1991. But basically, if you color the infinite structure, 2 colors or K colors, it's equivalent. And for 1 color, if you look at, this is in relational languages. So if you look at the structure, the age of that structure is the age of the original. So all of the finite structures embed into 1 color. So it's not quite the Ramsey property, right? And you could think about that you're, right, so age indivisibility, you could also say that for every A, there exists a B. Okay, and then when you color K colors, right, you're coloring the points K colors, and then you get a copy of A and B. That's all 1 color. Okay, so I guess they're trying to do with less, right? And they were able to do some nice calculations. You can look at their paper just using this age indivisibility. Another notion that they had in this previous paper, which was a definable self-similarity. So this is when in a non-algebraic 1 type over a finite set of parameters, that actually the realizations are isomorphic to the original. And we found that actually this notion, it predates, it goes back to Sauer's appendix to the Froissart's theory of relations. And so it's a nice property, and they're studying it and showing that that could be used to simplify calculations with these ranks. So actually, I won't be talking about the definable self-similarity today, but just a little shout out if you're interested. I want to look at that earlier paper too. So, okay.
Lynn, in this proposition, what is gamma? Who is gamma?
This should be the Froissart limit of K.
Oh.
And that's kind of a common notation they have throughout their paper. Thanks for asking. So what they do is they use age indivisibility to facilitate an argument that, say, the rank from the class of equivalence, finite equivalence relations, and DP rank differ in a specific NIP theory. Okay, so that's the motivation. And when they look at the classes, for ages that they know about, they find that they sit nicely in this linear order, but in general, it should be a partial order of classes. And so they're wondering, are there any other ones? Do the classes remain linearly ordered? Is there some reason for that to be the case? So we were on the hunt for classes, basically, and it became a very general investigation. Okay, so that's motivation number 2. Well, I guess I'll burst the bubble at the beginning that there's no answer yet, because we looked at some products on classes, but they're just giving intersections of classes in this order. So for example, if you're thinking, well, how could I put linear orders, if you admit a linear order and a graph relation, could you find something different with these products? And the answer is no. So for that question, it wasn't a real success. but I think independently, we might still be able to simplify some calculations on ranks, and maybe these are results of independent interest. Okay, so that's my sort of 15-minute introduction, because I think it might be unclear how we got to this place. Why did we start thinking of these questions? And I think for the long answer, one probably needs to read Vince and Miriam's prior paper. So in our work, we just kind of take it as a given that it would be interesting to understand these partition properties on classes. Okay, so here we go into partition properties. So we take as our definition the following for age indivisibility. So for every A and number of colors, you should be able to find B. And then no matter how you color B with the points from B with K colors, you can embed A into B in some way so that the image just lands into one color. And in the El-Zahar and Sauer paper, they say B is a Ramsey element for A. Now this is equivalent to coloring the points in an infinite structure with that age. 2 colors, if you like, it's equivalent to K colors, and then within one color, right, you're getting all the finite structures embedded that should embed in M. So from here on out, our languages are relational.
What is the relation with between this and Ramsey? Which is stronger?
Well, so the Ramsey property would be for all A, for all K, right? For all B, right? So for all A and B, because you're looking for, you're coloring.
Yeah, I know it's different. For all
right?
A and B, there exists C such as
Yeah.
but is there any implication on between this and this?
Well, one thing that I noticed is if you have different one types, there's no hope, right? So it's so sometimes in Sauer's work, there's that assumption that the automorphism group is transitive on elements of the model. So if in order to be age indivisible, you need that. You need just one, right? One type. Otherwise, you could color according to the type, and then you wouldn't.
Excuse me, Lynn.
Yes.
Hi, it's Anand here.
Hello.
Isn't there a version of this where you ask that the age of the pre-image is actually isomorphic to M? Isn't there some version of these?
Yeah, and I was actually going to ask for some help with the history, because there's an indivisibility, which the word I think dates back to labor. He uses indecomposable, maybe further back, and I just don't know. I see.
Okay.
Yeah.
Yeah, thanks. Okay, that's the relation. Yeah. Okay.
So
this definition is not equivalent to the previous one, right? Oh, it is.
okay, this one is not. So if you can find the whole thing, right? I think I understood the question. If you can find the whole structure inside, an embedding of the whole structure with one color, that will imply age indivisibility, but not the other way around. And so the next slide is a counterexample. So, sorry, I feel like I rushed ahead. So there was the question from Itai, right? So,
yeah,
right.
the question was whether any implication goes. So
Yeah. So let's see. So for Ramsey, A is just you're coloring a point, right? And the thing is, for Ramsey, I think you could have the Ramsey property, but not this, because you have points of 2 flavors. So maybe this is one with P0 and then points of this flavor. And this one can be red and this one can be blue, and then you've succeeded. Right? It just needs to be that for the same one type, you get the same color. But I think we're asking for something a little bit stronger with the age indivisibility, that this would all come to one color. All the points have to be one color. So I would like to say that Ramsey property implies age indivisible, but it doesn't. Right, and then clear.
Other direction also.
I think this, I haven't thought about it carefully, but I think there's no hope, because how would you get to any, you know, like all structures just from points? So that one, it never occurred to me that it could go that way. But hey, if for some structures it did, that would be something cool about the language, right? Like it's very granular. So to my knowledge, right, we don't have.
Yeah, okay, I
this
see.
one.
So right, so there shouldn't be any reason.
Yeah, I don't
some,
think so.
Some examples like DLO, for example, right? This is both Ramsey and age indivisible, right?
Yeah, and later on, I'm going to talk about, there's some really nice work starting, well, maybe even before this, but the paper with Kojman, Hassan, Anshus, and they're looking at a different kind of indivisibility, symmetrical indivisibility. And they prove that it does hold for DLO as well. So sort of a stronger condition as well. So yeah, it's kind of a mystery, right? So you have the same theory that is able to take on these 2 or 3 properties, but in general, you don't really see, right? So at least for me, I feel like there would be no hope this way. And then for this way, the issue is the Ramsey property is asking for less than age indivisibility. So yeah, I think these are really nice properties, and I think it's really nice to see, you know, like these papers I'll mention, not just the Hassan Kojman Anshus paper, but with Bodirski and Miodrag Sokic, and they're applying these model theoretic techniques to these properties. Really nice. Okay. So, all right. Yeah. So in terms of the implications here, so this one should be relatively easy. Let's see. So countable structure, if you can find the whole structure inside, right, then you should be able to use this definition of age indivisibility, where you color with the 2 colors, and then for one of the colors, you should get the entire age. Because, well, you had an embedded copy of the whole thing in there, so I think you should get that. But you might like the next example. And I want to say that throughout this work, my colleague, Miriam Parnas, is a wizard with counterexamples, and she's coming up with these strange classes without the hereditary property, without joint embedding, lots of interesting graph classes. So really grateful to all the examples she came up with. Okay, so for this one, let's try to argue that it's age indivisible, but it's not indivisible. So what we have here is a grid, omega by omega. I'm thinking about how my calculus students would feel about this. I actually dressed up as omega for Halloween, but I only put some of the numbers on me. So, okay, so we have omega going both ways, and we have these 2 equivalence relations, right? So these are the E0 classes, and then the other way, these are the E1 classes. And maybe we should start with number 2 here. So consider coloring of this infinite structure according to the diagonal. So if you're under the diagonal, you're one color, or if you are or over the diagonal, you're another, then how are you going to get an infinite substructure that's isomorphic to the original? So eventually you would run into that diagonal. But we can also make an age indivisibility argument. And I have to admit that I was stumbling on this one, and we had a more general proof, but I felt like there should be something more simple. So, but Vince and Miriam were explaining it to me, that you could make it simple. Say you're just looking for the n by n grid. So I guess these are these cross-cutting equivalence relations, and within an E0 class, you have these inequivalent E1 inequivalent singletons. So it would suffice to look for something like this to find any type of finite substructure. So I believe the idea is that maybe just take a little swath here of length 2n+1, and then you decide who's majority red and who's majority blue within that swath. And then you're going to say, yeah, but you don't know if it's on the same coordinates. Well, say you have an infinite subsequence that's majority red without loss of generality. So now just focus on that subsequence. Now the actual coordinates, right? The sequence here, how does it go red, blue, or 0, 1, 0, 1? There are finitely many ways to be, but you have an infinite sequence. So then you do another pigeonhole property so that you've really uniformized, not just that it's majority red, but red on these for some subsequence. And then you get your red box. What do you think? Does it hold water?
But what was the definition of age indivisibility? It was, you needed a countable structure, no, in the end?
For that's indivisibility without the age on it.
So what does, again, can you remind us what does age indivisibility mean?
Yeah, so age indivisibility is for any finite structure A. I need to find a monochromatic A in the infinite structure.
For any color you want.
Yeah, so we can do two. So let's say for any coloring of the infinite structure, two colors, oops, there is an embedding A into M, right? And the image of A is just going to be one color.
But another question is, what if you take the first limit of this class? Then it is, I think. Then what can you say about this? It's still indivisible. Maybe it is indivisible.
Yeah, no, this is a good question. I was thinking about this this morning, and this is going to sound weird, but I think this is the Frisé limit.
Oh.
And I was going to check with my co-authors because I've been a little bit falling down this week, right? There's some crazy COVID things happening. So apologize if I'm making a mistake here. But so what we talk about later is that there's a product. Bodirski calls it the full product. And so I just write M equals because it's an infinite set in the language of pure equality. And so this is the structure. So Bodirski defines it a little bit differently, but it's not just interdefinable. It sort of is the structure and how we define it. And so we show that actually the Frisé limit commutes with this product. So the Frisé limit of this and this would be, oh, I guess I should put the class, right? This is the class of finite sets. Okay. Class of all finite sets. So this is this. So in fact, I believe what we have here is a Frisé limit. There's no linear ordering. So the finite substructure should be saying that you have these cross-cutting equivalence relations, but in so doing, there's right at exactly one point in each equivalence class? In which case this omega structure, when I checked it in my head, should satisfy it. But then also there's this proof, right, that we have in the paper that it should be the Frise limit. This is a
Okay,
very,
this makes sense. Yes. Okay.
this feels very weird to me because I always think about the Ramsey property and I just always put a linear ordering in it because you need this rigidity. And so to start thinking about age and divisibility, I feel disoriented because it's just coloring the points. I don't know. It's really new to me, but it's a cool area. I've been reading a lot of people, and so I enjoy that part of it. Okay. All right. Okay, so let's jump off here. So there's this this certain kind of product, and people are calling it different names, and I don't know if our name will stick at all, but this was a composition in Hassan, Kojman, and Anshus, and Sokic's paper, it calls it LEC. So you have a class L and a class K, and you put them together in this way with an equivalence relation. And he points out in his paper that, you know, you should see that the if you have actually Frise classes, that the automorphism group of the Frise limit should actually be this wreath product of automorphism groups. And then I was looking for kind of a nice exposition, and thankful to Dugald McPherson, who pointed me to this Peter Cameron paper. So we just work it out in our paper that this is so. And I'll point out that the Hassan, Kojman, Anshus paper, it's doing something more difficult than what we're doing. They're looking for symmetrically indivisible structures. So it would be an embedding of the infinite structure such that all automorphisms of the embedded structure lift. There's a cool property. So sometimes they're, you know, assuming more things, I think, to get that. And then, of course, they could have gotten the easier one too, I think, but why don't we just argue it on the next slide? So, okay, so how is the wreath product? So you have this sort of outside structure. This is the way I think about it. B is going this way. And then for every coordinate, you have an equivalence class. I think it's very natural to think the points of B would be blown up to be equivalence classes. And then, so for each of these, you have some structure, and maybe it's copies of the same structure, though in general, it could just be different for each B. Our application is when they're the same. And so in this paper, we use the universe from this paper. And so basically, I think a way to think about it is, again, that these are the indices, right? So in the outside language, a relation there would hold on pairs if it just holds here. So I don't care at all what the points in here are. And let's just make the languages disjoint if they're not already. L0 and L1. Okay, but then if you're within a class, right? So if your B's, your indices B0, B1, they're all the same and you're just in one class, then for the language of A, you just do whatever A would have done. And then we define an equivalence relation, and it's just your equivalent if you share the same index here. So we'd like to think of the putting the two together, and we chose wreath product because sometimes we want to talk about the automorphism groups too. And so you can, get this nice thing that the automorphism group of these is the wreath of aught A and aught B. And okay, so it tells a little bit of the story of how I got into this project. So if if you had had A and B with a definable ordering, each with a Ramsey property, then the product would have it. And it follows due to calculation of automorphism groups and the Kekres-Pestov-Todorcevich technique that from the automorphism group, you can tell the Ramsey property of the class. But I had been kind of inspired by this argument for the strong tree indiscernibles modeling property when I was working with Byung-Han and Hyungjin Kim, which was in turn based on the Shalaf arguments, just made them countable. And so I wrote a finitary argument for this, that really based on those. So what I think of when I read Shalaf's arguments is like, okay, you color according to these one colors, and then the colors are tuples, right? And then you uniformize on the tuple. And it seems to be a specific way of arguing that's a little bit different from the partite construction. So Sokich in an earlier paper argues for the same thing using a partite construction. And I think it's interesting because one, you change the number of colors and it's, you know, it's one sort of specific way of doing it, and the other is sort of traces more back to the Neschetl-Rodel argument. So anyway, I had thought that, you know, that's really nice with the Rieth products and characterized NIP theories by collapse of the indiscernibles, and thought I was really clever, but actually it's true in general that the class characterized by this kind of product of two ages, you don't get anything different. So what I obtained in my previous solo paper holds generally. Okay, so that's kind of how I got on the project. And
So the generally means without NIP, right? That's what you mean by generally.
yeah, so this one, I mean, I had thought the class K would be the age of this one.
But when you say generally, you mean for every class and also without NIP?
Yes.
Okay.
Okay, yeah, I think the assumptions are finite structures, class of finite structures closed under automorphism. So pretty tame. And I believe that, you know, relational, right? And then no other assumptions for this one. Now, sometimes in the paper, one has to look closely because we assumed hereditary property or we assume joint embedding property, but I'm seeing not for this result. Okay, so let's just work through this argument. I think it really gives us a taste of all of the arguments. So, so it was stated in the Hassan Kocaman and Onsh's paper as an easy modification of a harder theorem that they were trying to prove. And I think it's so easy that one doesn't need sort of these additional assumptions there. I'm sure they would agree. So why don't we just go through it, because it will just take this little piece of paper. So if you have two structures and possibly different languages and you make the signatures disjoint, and each of those are indivisible, then the Rieth product of structures should be as well. So, so this is the one that Anand was talking about, right? You're trying to find the whole structure in there. So let's color. We could say K or two colors. There's no real benefit either way. So then we just say K colors. And we're going to define these, the colors on the classes. So again, B is kind of like the index, right? And then for each B and B, you have a class, which is going to be a copy of A. So let's define the coloring just in one of those classes. So for B and B, CB is how those, right? So CB is a, all right, let's be careful, Lynn. I'm just drowning in punctuation here. Okay, so let's put the colon there because it's a function. So it's going to color points from A. So in the natural way, the way that this one is colored. So this specific thing is A comma B. So A from A, B from B. And we can think of what arises as a coloring of A. Okay, so now we'll start using our assumptions, right? So A is indivisible. So there is a color such that for some copy of A, right? So we get a copy of A and it's just going to be this one color. Under the coloring, you just get that one color. So it's like we're applying the indivisibility in each of these classes. And then kind of like the previous argument, we sort of want to uniformize across B. So let's also define a coloring on B. And it's going to be according to sort of what you got in each class. Okay, so now we can reach into our B, the fact that B is indivisible. So there is a color for this coloring. For some copy of B in B that we're just going to be hitting that one color. Well, that's kind of what we needed. So we're just going to set, we'll have a new structure, which is going to be, oops, these guys, right? It's isomorphic to the original, contained in the original. And let's argue that it's all one color. So I think the visual works pretty well. So for each of these, you have some color I of B, right? A copy inside, that's I of B, copy of A. I don't know, maybe I should say I of B1, I of B2, I of B3. But then you're now coloring these points according to what was I of B. And then by indivisibility of B, you should be able to choose a copy of B, which we'll call D, and then those points are the same color. So now you just put together these pieces and you get a copy of the original, but it's all the points in that copy are one color. So what do we think? Does it hold water? I have a friend from New York who always used to say that. Does the argument hold water? The argument is not a bucket.
Is it a trap because it looks fine?
Yeah. I love these analogies, bad math analogies. So long as it's not a sports analogy, it's not as bad as it could be, is my view. Okay. All right. So anyway, we just put that out there. I mean, I think it's clear that you don't need any special assumptions other than relational. Okay, and I know I just have a few minutes left, so I really think the spirit of the argument is here, and you could probably come up with the arguments yourselves for the next few. And in fact, you'll have to unless you read the paper because I don't have time to talk about it. But okay, so then you can make an argument that's just for the ages. So what would the age of this be, right? So you would just take all the finite structures that look like this. So for some finite set of indices from the first class, and then some bubbles from the 0 class. And an argument like this works. So you do need joint embedding in K0, because there's some point where you want to say within the A that there's some big enough structure that contains all the possible things that could be there. And we actually have a counterexample when you don't have the joint embedding in there. But so subject to some mild assumptions, the age indivisibility is preserved. Okay, so this is this is part of Miriam's wizardry. I mean, these things are monsters. They're just anyway. So you have these two graph relations, and okay, what in God's name are we saying here? So for a finite graph, you're not going to have edges of both types. Can we call these red and blue edges? So you can have this, you can have this. You just can't have both. And then you put that together into a class of finite structures closed under isomorphism, but it's going to fail JEP, because if you try to put these things together into one structure, you've violated this condition. Okay, but what's interesting is you still retain age indivisibility. And you almost want to make a political analogy in the United States, right? So to find the blue, you just look in blue, and to find the red, you just look in red. So the age indivisibility of graphs, which the indivisibility for graphs was proved a long time ago, right? I think by Sauer and maybe a co-author. So sorry, that's not coming to me right now. But then the age indivisibility follows, and then you just look in your respective political party. Okay. Now let's make the Riesz product with just all finite sets. So we're going to have finite sets going this way. So this is not going to work out because of A equals, I realize this should probably be my last thing. Okay. So I'd actually like to color a point. Let's see, color red if attached to a red edge. Right, so if you're going to find a copy of A, all of whose points are one color, then you have a red edge here. So these guys are going to have to be red. But then I guess these guys are going to be too. But no, you can't have a red edge there. Or you can't have any kind of red edge coming out of it. So there's no monochromatic copy of A. So that's kind of neat, just on the level of ages. Okay, so I think I won't be talking about the direct product of structures today, but it's coming from the full product in Wodierski, and I'll just mention that he was using that to prove this preservation of the Ramsey property for classes with strong amalgamation. And so we were just investigating preservation of age indivisibility. So for the age indivisibility, we're good, but actually not for the indivisibility. And that's that first example that I presented with the classes going this way and going this way. Okay, because the infinite thing was not indivisible, even though just infinite set is indivisible. So there's a open question that we'd like to see solved. So what about this free superposition? So the idea is take something in this language, something in this language, choose to glue it together in some way and make the class of all of those. Does that preserve age indivisibility? Just don't know. Okay, well, bunch of references that came up. Sorry that they're going into a bunch of different slides here. It's a really nice area. It's been going on for some time, and it'd be interesting to see the answer to this question. So anyway, thanks so much for listening, and really enjoyed it.
Thank you. Thank you. Is there any questions? From the people online, maybe? So thank you again.
Oh, Nada.
Oh, sorry.
I wasn't sure if he was waving to me.
Yeah.
I've been on
Yeah.
Zoom for a year, and I like.
Yeah. I guess maybe a couple of comments. Yeah, actually, I have a paper that the result about the indivisibility of the what you called wreath products.
Oh.
I actually called it lexicographic products.
Oh.
It's there. Yeah, right. Exactly as you said, without any assumptions about accountability or anything like that. However, yeah, I think, okay, maybe that's a question. I think you should assume or otherwise deal with the definition somehow. You need to assume that there are no unary predicates in the language. So that's a question, I guess. And another comment / question, just to make sure yeah. So regarding what...
Nadav, what is the question about not having a unary predicate? What is the question?
So I think, so maybe, okay, the first question is, do you assume in your results that there are no unary predicates, or how do you deal with unary predicates? Because I think I have an example with if the language, I don't remember now because it's been a while, but I think if L1 does have unary predicates, then the indivisibility is not preserved.
Yeah. Okay. So we should definitely talk about that. So thanks for letting us know. We'll put your name in the revised version. My initial thought is that if you assume indivisibility of the input structures, then there's.
Oh, right. Sure. Yes.
Yeah.
You're right. Sorry. Yeah, I thought about a different. Yeah, right. You're right. Yeah, sorry.
But this is interesting. I mean, like I said, I'm getting to know the area. I've done a lot of reading. I need to do some more reading. So I'd be interested to talk more. Okay, so we'll be in touch, I guess. And the second question / comment is regarding the relation between the Ramsey prop. So first of all, I guess regarding the implication from age indivisibility to the Ramsey property, if you're talking about the embedding Ramsey property, the one which enforces the structures to be rigid or have some order or something like that, then obviously, in an obvious sense, it does not imply age indivisibility. Doesn't imply this property because graphs have age indivisibility, as you said, and graphs don't have an order. So you get that. And that's good. Yeah.
For the other direction, I guess, I think you said that, but I'm not sure if the audience or specifically Itai caught that. And just to make clear, I think that if you're talking about structures, the class of structures which have only one type or something like equivalently, it's a Fresset class which has a transitive automorphism group, then RP implies age indivisibility, right? Because
then I think so, yeah, because I can only think of this counter example if you have two unary predicates, right? And they're just infinite.
So I guess the analog here is like instead of, so you need to replace the names of the structures, right? Instead of A and B, you call them B and C in the Ramsey as in the Ramsey property, and then A is just the structure with 1 point, right?
Yeah. So C then would be just 1 point, assuming there's only
Yes.
one of this type in the class, right?
Yes.
Up to isomorphism, K colors. Yes, I think this is my suspicion, but I didn't verify that. Yeah, if you just had the transitivity of the automorphism group, maybe it just followed.
But how do you use the transitivity in the end to show that actually you get the same age?
No, so the transitivity says that there is only, so transitivity implies that coloring points and coloring the structures of, it's the same as coloring the unique structure of size 1, right? So in the Ramsey property, you are coloring structures or embeddings of structures, right? And then it's like, in that case, age invisibility is like saying that the Ramsey degree of this unique structure with 1 point is 1, which is like, yeah, I think Norbert Sauer called it like, actually, so age indivisibility is the definition of the Frese limit, and the analog is like vertex Ramsey property, and vertex is for like the, yeah, just the points of this structure. So just, yeah. Does that make sense?
Yeah, sure. So, right. So yeah, so that now you know that if you have a cell limit of transitive, if the Frese limit is transitive or has only one type, then Ramsey implies age. Yeah, that seems correct. Yes. Yeah,
so maybe actually, now that I got into it, I remember the question that I had just from reading the abstract. I don't know if it makes sense, but I don't think it's been ever looked at, but as an analog to the Ramsey property, you have this property of having finite Ramsey degrees, right? So I guess it would make sense to ask some questions about having finite age indivisibility degrees, probably not such a good name, but I guess you understand what I mean.
Yeah, why? Right, because these persistent partitions, right, in the work of Sauer and co-authors, like maybe there's something there.
Yeah, and I mean, recently there's been work by Andy Zucker that proved that if you have finite Ramsey degrees, it's equivalent to having a pre-compact Ramsey expansion. So maybe there could be an analog result in the age indivisibility sense, but that's just a wild guess. So yeah, I have no intuition as to whether or not that's true.
That's really interesting. And I also, is there anything we know about the automorphism group of a Frese limit of an age indivisible age? You know, like the KPT. I was looking, but I wasn't finding. So that would be an interesting question.
Yeah.
We already talked about the transitivity of the action. Is there something else we can say?
Okay, thanks.
Yeah. Thank you for the information and the questions.
Thank you. Are there any other questions?
Actually, another kind of question is whether there is anything that age indivisibility says about the automorphism group.
Yes. Yeah, that's a good question.
Yeah. So you don't know, right?
No, I haven't seen anything. And then, I was hoping maybe you'd have something from the Ramsey property, but as we said, it doesn't look like it quite lines up.
Any other questions? Thank you again for the talk.
Thank you so much for having me. Thanks.